Welcome back. Now, we're going to take what we know about the vertex, the axis of symmetry, zeros or x-intercepts, a y-intercept, relative extrema, and we're going to combine all of that together to analyze, list all of the attributes, and then graph this quadratic function. So we're going to be synthesizing quite a lot of information that we already know and pulling it all together to use it for one problem. You will definitely see a problem that looks like this on your test where you have to do all of these things for a certain quadratic function. So let's start. The first thing we're going to do is we're going to start with our new information. We're going to state the vertex. And we need to know the formula for finding a vertex. The first thing we do is we find that x. X is negative b over 2a. And once we have that, we're going to take that negative b over 2a, plug it into the function. That will give us our output y value. In this situation, my a is negative 1. My b value is positive 8. So my vertex, the x value of my vertex, x equals negative 8 divided by 2 times negative 1. That gives me an output of positive 4. Negative 8 over negative 2 is 4. Now we'll find the y value by taking that 4 and plugging it into the function. So that is negative 4 squared plus 8 times 4 minus 15. So my y value, or f of 4, is negative 16 plus 32 minus 15. So that is negative 31 plus 32. That gives me 1. That means my vertex is the ordered pair 4, 1. I'm going to clean the screen up a little bit. So I've written my vertex 4, 1 as an ordered pair up here. For part B, we're going to find the axis of symmetry. Now remember, the axis of symmetry passes through the vertex. The axis of symmetry is always a vertical line. The equation of a vertical line is x equals some number. What does that x value equal in the vertex? And the answer is 4. So the axis of symmetry occurs at x equals 4. For part C, we're going to determine if this function has any relative extreme values. And by relative extreme values, that means we are looking for a max or a min. Well, we know that all quadratic functions are shaped like parabolas, and parabolas either open up like a cup or down like a frown. And that can be determined by looking at the leading coefficient. In this situation, a is equal to negative 1, which is less than 0 or negative. So since that a value is negative, we know that the graph opens down like a frown. If it opens down, that means it has a maximum. So as I just said, the graph opens down, and if it opens down, it has a max at the vertex. Remember, when we state max or min values, the max or min is y, and it occurs at x equals some number. So in this situation, we'll say the max is the y value 1, and it occurs at x equals 4. Again, I'm going to clean my screen up here. So now we state that the maximum is 1 and it occurs at x equals 4. Part D, we're going to determine the zeros of the function. And zeros, by definition, we learned this very early on in the semester, but zeros occur where f of x is equal to 0. So if you're asked to find zeros, that means you take the function and set it equal to 0. In this case, that's saying 0 equals negative x squared plus 8x minus 15. What we have here is a quadratic equation, and we need to solve this quadratic equation equal to 0. Now, if I take this -1 and multiply it by 15, that gives me positive 15. And are there two factors of positive 15 that add up to equal 8? The answer is yes. We have positive 5 and positive 3. So that means this is factorable, and we can factor this quadratic equation to find the zeros. I'm going to use that bottoms up method. So I'm going to multiply that last term by -1, turn it positive. My two factors of 15 that add to equal positive 8 are 5 and 3. So I have 0, I've got x plus 3, x plus 5. Now, because I multiplied by the -1, I have to divide both of these by -1. And that is 0. We've got x minus 3 and x minus 5. That lets me know that the zeros of this quadratic function are x equals positive 3 and x equals positive 5. Again, I'm going to clean up my screen. So I list the zeros here saying x equals 3 or 5. If I was asked to state the x-intercepts is a little bit different, but the same as the zeros. We'll say 3, 0, and 5, 0. If we are asked about x-intercepts, an x-intercept is an ordered pair. So you're going to state 3, 0, and 5, 0. The y value is always 0 for the x-intercept. And that was what we just solved. We said f of x equals 0, which is the same as y equals 0. So these are my two x-intercepts. Now we'll look at finding the y-intercept. Whenever we want to find y-intercepts, we let x equal 0. So we're going to calculate f of 0. F of 0 is negative 0 squared plus 8 times 0 minus 15. We get that f of 0 is negative 15. So my ordered pair for the y-intercept is 0, negative 15. Remember, when you're stating those and you get this function notation, f of x equals y. F of 0 is x equals y, negative 15. So that's my ordered pair for the y-intercept. One thing you may notice, this negative 15 value, it's the same as the constant value. It's always going to be the constant, just like when we're dealing with a linear function. That constant, y equals mx plus b, the constant, is the y-intercept. In quadratic functions, c, the constant, is the y-intercept. At this point, we've listed 6 different attributes of the quadratic function. So we've described or analyzed all of the different characteristics that we know. So for part G, we're going to create a graph. When we create our graph, we can draw or scale our axes however we'd like. On my x-axis, I've made my tick marks a little wider apart. I'm going to count 1, 2, 3, 4, 5, 6, 7, and 8. And then on my y-axis, since I have to go all the way down to y equals negative 15, I've decided to count by 2. So we've got negative 2, negative 4, negative 6, negative 8, etc. So now that I've written out my axes, I'm going to go ahead and plot my y-intercept. So my y-intercept's at negative 15, which is between negative 14 and negative 16. Where are the x-intercepts? Well, the x-intercepts are at +3 and +5. Lastly, we had one other point. We had a vertex at 4 up 1, so right about here. So here is the space for our graph. Of course, we know it's shaped like a parabola. We also know that it is symmetric. Parabolas are curved. They are not V-shaped. So whenever you're drawing these on your paper, it doesn't have to be perfect, but I do want to make sure that you're not drawing a V. You're not going, all right, I'm going to connect these up here, sharp point. A sharp point is not good. Now, I want to talk about the fact that we know there's a vertical axis of symmetry which passes through the vertex. Well, by the axis of symmetry, we know that this point was 15 units down and 4 units to the left of that axis. So 15 units down and 4 units to the right. That's going to give me another point on my graph, right? So this was 4 units. If we went 4 units this way, we get to a point right here below +8. So just talking about this graph and these points, when you draw it again, I want this to be a smooth curve, no sharp V's. You make it look like a V, that would you'd end up losing points in that situation. I also want you to always list your important points on the graph. So we have 0, -15. Up here I had 3, 0, and 5, 0. My vertex was at 4, 1. And then I also graphed this other point over here at 8, -15. And we found this 5th point on our graph by using what we know about symmetry. So we have a couple more parts that we're going to look at, and this is really all review, again, taking previous knowledge and pulling this into our quadratic section. So let's talk about intervals of increasing or decreasing. Remember, we read a graph from left to right as it travels across the page. And as we read this, obviously it is increasing until the point where we reach the vertex, and then we turn around and we begin decreasing. So now remember, we always state intervals of increasing or decreasing using horizontal x regions. So we are increasing from -infinity, all the way until we get to x equals 4. And then at x equals 4, we begin decreasing until we get to +infinity. So remember, intervals of increasing and decreasing, those are always x intervals. We're saying everywhere to the left of 4 is increasing, everywhere to the right of 4 is decreasing. When we talk about increasing and decreasing, this is the only time we don't have to think bracket or parentheses, because increasing and decreasing intervals are always open. And of course, for our last two parts, this problem wouldn't be complete unless we talked about the domain and range. Now remember, domain is the horizontal span, and it does appear that the graph goes to the left and right forever. So my domain here is all real numbers, that x is in the set from -infinity to +infinity. What about the range though? The range has to do with the y values. So that's up and down, my vertical span. Does the graph go up forever? And the answer is no. We have a top, a maximum y value, which is 1. Does the graph go down forever? The answer is yes. So my range is -infinity to 1. And we have to say, well, are we allowed to touch that value where y, my maximum y, is equal to 1? And the answer is yes, we can. It's a point which is defined on the graph. So the maximum here occurs at 1, 1 is included as the maximum of our range set. So that's, a really good comprehensive problem of taking all of this knowledge and talking about it simultaneously, essentially synthesizing everything we know. So in this problem, we analyzed a quadratic function. We found the vertex, the axis of symmetry. We stated the relative extrema. We stated the zeros, the x-intercept, the y-intercept. We created the graph. And then we brought in previous knowledge about increasing, decreasing intervals, as well as domain and range. As always, if you have any questions, please feel free to email me.